All right, so in the previous video, I showed you that the work done by the gravitational force was equal to the negative change in a potential energy. Okay, it was negative because the displacement and the force were in opposite directions. I wanted to do a short numerical example of this, right? Using this fact and the fact that work is positive the change in kinetic energy, right? Simultaneously, it is both of these things. So let's, for example, say that some object starts on the ground at height 0 with a speed of 10 meters per second, for example. All right, 10 meters per second. And we wanted to find the height h. You could have done this back in chapter 2, right? This really is just a one-dimensional constant acceleration problem. So let's do that real quick, right? Pause on chapter 7 stuff and let's go back to the chapter 2 method, right? Basically 1D kinematics. So we don't necessarily have a time, but that's okay. We have an initial speed specified, and that's really all that matters if we want to find a total height. So the equation to use is the final vertical speed equals the initial vertical speeds, both of those squared, minus 2g times delta y, right? Y minus y naught. And so we're solving for the final height y. And so what can cancel out? Well, if we start at the ground, that's 0. And if it goes up to its apex, right, the maximum height, the final vertical speed is also 0. And so what we have is 2gy equals v naught y squared, and y equals v naught y squared over 2g. So if we plug in the initial speed of 10, that's 10 squared over 2 times 9.81. See, that's about, well, let's see, 2g is about 10, right, about 10. So that's a factor of 10 over 10. That's about 10 over 2. So that's approximately, what is that? 5. About 5, right? Now let's do it the chapter 7 method using work and energy. Okay? So I said above, work is equal to positive delta K. It's also equal to negative delta U. We just found what that's equal to right there, right? As this object is moving up, the force of gravity is acting downwards on it, and we got a negative mg times the total height h, right? I know over here I called it y, sorry, but actually that should be h. So let's do that here. We have negative mg, I'll do y here to stay consistent, and then that's equal to the change in kinetic energy, which is 1/2 m final speed squared minus the initial speed squared. Okay, well, let's solve for y. First, can we cancel anything out? Well, masses go away. That's on both sides. And if it's going up to a stop at the maximum height, the final speed is squared. The final speed is 0. That goes away. And so we have y equals, well, negative gy equals negative v naught squared over 2. Can you see what's going to happen? The negatives go away, and we have y equals the same expression as on the left. So that's also the same answer. It's the same expression, but two different ways. One uses work and energy, and the other uses kinematics, right? Really, they're from the exact same source, right? They come from the same definitions of speed and acceleration, right? But I would argue that this method is much easier than having to remember, what was it, 5 of those different equations and remembering to input the sign accordingly, right? Just remember this and you're good to go, right? Assuming you remember the fact that potential energy has the form of mass times gravity times some height, and kinetic energy has the form of 1/2 mv squared, you're good to go, all right? So this was an example of using the work and kinetic energy theorem, right, in conjunction with the fact that work is also equal to negative change in potential energy to get the final height of a projectile launched straight up. Okay? Thanks for watching.